Hey guys, I went ahead and created a support video for you guys so that if you needed some extra help understanding the notes, you can refer to this video. I will still have, all of us, all teachers, will still have our tutorial videos on our websites for you. We're going to post homework assignments, everything you need, like we normally do. Things will be a little bit, different than they were before. So we'll collect everything on Google Classroom. You can go ahead and print everything out. If you have a printer, you can print everything out, and then you can fill it out like you normally do, and then snap some pictures with your phone or borrow your parents' phone or someone's phone, and then you can use those pictures to turn it in as your assignment on Google Classroom. If you don't have a printer, you can use a separate sheet of paper. Just make sure everything's clearly numbered, okay, so we can see exactly which problems you're working on. Okay, make sure it's complete. It's a big part of what we're grading is making sure that you do all of the assignment. Okay, so here we go with Unit 11. Kinetics and equilibrium, and we'll go ahead and define these as we go through the presentation. So let's get started. Kinetics, the study of reaction rates. Okay, so kinetics in general is the study of motion, movement, and how things move around, right? So reaction rates involve that. They involve motion. Particles are coming together, they're colliding, they're breaking apart, they're reacting, right? And so that involves movement. So kinetics, specifically for this unit, we're gonna focus on reaction rates, and there are certain factors that affect reaction rates. Number one, concentration, right? For example, molarity, moles per liter, right, is a measure of concentration. So concentration and frequency of collisions. So when things collide with each other, right, they're banging into each other. The frequency of collisions, meaning, in other words, if something is frequently colliding, well, then there's probably a greater chance that the reaction is going to go quickly because these particles are quickly reacting. They're banging into each other very quickly, and so they can react. If they don't bang into each other very frequently, right, then the reaction would be a slower one. All right, but there are other factors involved in speed of reactions or reaction rates. So let's take a look at these bullet points here. A reaction cannot occur unless reacting particles physically collide. They have to bang into each other. Okay, if they don't come in contact with each other, then they're not going to bond with each other or cause each other to break apart or whatever the reaction involves. They also must collide with the correct orientation. In other words, they have to bump into each other at the correct angle. All right, otherwise a reaction in many cases will not work. So let's just take a look at, I'm just going to draw this out a little bit. Let me see if I can get this sketch tool going here. Okay, so let's just pretend we have a molecule shaped like this, for example, and we have another molecule shaped like this. And the reaction occurs when this molecule comes in contact with the inside of the other molecule right there. It wants to be in the very inside, and the product is formed like that. Let's just pretend that is how the reaction occurs. Well, if this particle is over here and it comes in at this angle, right, with this orientation, it's probably going to bounce off and keep going, or it's going to come this way, bounce off and keep going. No reaction will occur. It has to come in contact with the correct orientation, right, for that reaction to occur. And so that's what we mean when we say they must collide with the correct orientation. Okay? And then increasing the concentration leads to more collisions between reactants. So increasing the concentration, think about this. Let's pretend we have a container here. And this container has, our particle that we had before, and we have another reactant here. Now, if for these guys to react, let's pretend these are gases, and they're bouncing, they're moving around, bouncing around the container. Well, it's going to be a while before they finally hit each other with the correct angle or orientation. So this might take a while. But if we increase the concentration, let's just say of one of these reactants, let's say we increase the concentration of these guys, and we put a bunch more in there, right? Now all of these guys are bouncing around, right, the container, and there's a way better chance that one of these guys will lock in and bond with that other particle sooner versus if we just have a 1-to-1 ratio there. Okay, so that's what we're talking about when we say increasing the concentration leads to more collisions. Okay, and then of course the opposite would be true. Decreasing the concentration would lead to less collisions, therefore slow down the reaction. All right, moving on. Another thing that affects the rates of a reaction is the physical state. Take a look at the blue particles here. Having a big chunk of a reactant versus a ground up particular, like a particle-sized reactant particles, right? So these guys have more surface area exposed so that those green reactants can react with them. So for example, all sides of each little cube are exposed and available for these green guys to come and react. Whereas if they're clumped together, none of the surface area in the middle of this big chunk is exposed anymore. So that's going to lead to a slower reaction. Okay. Now let's take a look over here at this graph. Here's another example with calcium carbonate. Calcium carbonate, if you heat it up, it'll decompose, it'll break apart. And one of the products is carbon dioxide. So when we decompose over time, right, here's on the graph, the x-axis, when we decompose calcium carbonate, we can measure the amount of CO2 gas that is being produced over time. And if you take a look at both the red and the blue lines here, if we use calcium carbonate chips, which are larger pieces, similar to what we talked about with the big chunk here, that's going to be a slower reaction than if we use calcium carbonate powder, which are much more finely ground up. And so these little particles of calcium carbonate are going to react really quickly. So let's just pretend in time, this is time in terms of seconds. Let's just pretend this is, I don't know, let's just say this is 3 seconds, for example. Well, at 3 seconds, look at how much carbon dioxide was produced, right, with the calcium carbonate chips versus the amount of carbon dioxide that was produced with the powder, right? We have more powder, we have more carbon dioxide being produced by the powder at this time frame than the chip. So there's a much quicker reaction going on with the calcium carbonate powder. All right, so if you want to speed up a reaction, grind up any solids into more of a powdery substance. This way they have more surface area to react more quickly. All right, then another thing that affects reaction rates is temperature, right? In general, you heat it up, you speed it up. Okay, because you're giving it more energy by heating it up, and so those particles can move at a faster rate, and they can find each other, bang into each other more quickly and with more energy. So by doing that, you're going to speed up a reaction. This graph is very similar to the one we just saw earlier. Low temperature, you can see a slower reaction. With a higher temperature, right, you can see the reaction is speeding up. It's happening more quickly. Okay. All right, now catalysts. Catalysts can speed up a reaction without being used up. Enzymes are an example of that in biology. If you remember last year, enzymes are catalysts. They speed up reactions by lowering the activation energy. Now, technically, they don't really lower the activation energy. They cause an alternate pathway of the reaction to occur that lowers the a pathway with a lower activation energy, I should say. And let me give you an example of that. We're going to use our same two particles that we used before, right? This guy and this guy. So again, remember, this guy needs to fit, right? It needs to get in there and fit, squeeze itself in there to bond. Well, it needs a certain amount of energy to do that. That's what we would call the activation energy. If it's coming too slowly without enough energy, it might just kind of bounce off, or it might not be able to squeeze its way through to get into the bonding site and bond. All right, so therefore it's just nothing's gonna happen. All right, when this comes in contact with the other guy. So how do catalysts help? Well, let's take a look at this example, like a biological catalyst. Well, biological catalysts are enzymes are biological catalysts. And so I'm going to draw the enzyme as a blue blob here, right? They kind of look globular like that sometimes. In any case, so what happens is, rather than these two guys just coming together on their own, an extra step is involved, hence the new pathway. An extra step is involved. So the catalyst can grab onto this reactant, and when it bonds to it, it can cause a change in its shape. And so, in other words, this guy is no longer going to look like that. Rather, it'll stretch it open a little bit. It'll stretch it open a little bit so that this guy has a way easier time getting in there. So not as much energy is needed to get into the bonding site where it needs to go. And that is what we mean when we say that it provides an alternate pathway of lower activation energy. Okay, and we can see that with this graph here. With a catalyzed reaction, with that enzyme, there's less energy needed. This is a potential energy diagram, also known as a reaction curve diagram. And this is the amount of energy the reactants were starting with. This is kind of the energy they were holding, based on temperature and some other things. And so they needed to have a certain amount of energy, right, in order to come together to finally make the products. Well, with a catalyst, they only need a little bit of energy because in this case, the enzyme is holding this guy in a certain position to make it real easy for this guy to go in with very little energy. But if you have an uncatalyzed reaction represented by the blue line here, well, that requires way more energy. As you can see, a lot more energy is involved. Why? Because without this enzyme, this guy doesn't look like this anymore, right? This guy is going to have that other shape, its original shape like this, right? Where it forces this guy to kind of squeeze through, requiring more energy. All right, that's just one example. There are many, many different types of examples of how a catalyst can speed up a reaction. That's just one example so you can understand how it can, result in a different pathway that lowers activation energy. Okay, so now catalysts do speed up reactions in both ways in a reversible reaction. So we'll talk more about reversible reactions later when we discuss equilibrium. Just know that reactions that occur can happen in two directions. Just as a real quick example, let's say we have A and B coming together to create a synthesis reaction, right? And sorry, I'm using I don't have my stylus, so I'm using the mouse as a drawing tool, which is not very efficient. Okay, there we go. All right, so we have this coming together to make this. Well, that's a reaction, right? It's a synthesis reaction, combination reaction, but that doesn't mean that AB can't break apart back into this again, right? So that would be a reversible reaction. So we can use a double-sided arrow to represent that. So if this breaks apart and becomes this, well, then we're going in this direction, right, as that decomposes, right? So these guys can come together to make this guy can decompose to make this. So this is what we call a reversible reaction. All right, so in general, whenever you add a catalyst, it's going to speed up rates of reaction, but it'll speed it up in both directions. And that's what they're talking about here, both ways in a reversible reaction. Okay, so let's talk about reaction rate, changing concentration over time. Now, the Greek letter delta, right, symbolized by this triangle here, that's the Greek letter delta. This is the change or difference in concentration. So the difference meaning the final concentration minus the initial concentration of some substance, okay, over the change in time, all right? So the change in time would be your final time minus your initial time, or something related to that. How much time has passed, basically, since the beginning, since you started tracking the reaction to the end when you stopped tracking the reaction. Okay, that's what this represents. Now, these brackets are here on purpose. These brackets represent concentration. And for this unit, anytime you have a substance inside these brackets, what we are explaining to you, we're trying to show you, is that we are talking about concentration and specifically molarity. Okay, so molarity, if you remember, right, capital M equals moles per liter. I know it's so slow, it's painful for me too. Okay, all right, so this is molarity, moles per liter, right? So that's really what we're going to focus on in this unit. I know there are different ways of representing, concentration, molality, and some other ways, but in this unit, anytime you see those brackets, moles per liter, okay? All right, so we have change in concentration of substance A over time, right? This is essentially how you would calculate that, by doing the math here, okay? All right, so here's an example of iodine and hydrogen, diatomic iodine and hydrogen coming together to create hydrogen iodide. Now, as the reaction progresses, you're using this up. So in other words, you don't have any, in the beginning, you have no product, right? No product. You're combining these two in whatever amounts you have, and these guys are going to get used up as this is being created. And that's what's represented by the blue and red lines here. So let's take a look at the reactant side of this. This is the red line, all right? The reactant side, these guys, the concentration of these guys is going down. Why? Because they're being used up in the reaction. And so the blue line, if you take a look at it, is going up at a curve in this way because it's being produced. But notice the coefficients, right? Here you have an invisible 1, 1, and a 2. So we have a 1 to 2 ratio here. And so if you look carefully at the graph, let's just pick a moment in time. Let's just pick, let's say this moment in time. Let's just pretend that this is 3 seconds, okay? Well, 3 seconds would be right about here, okay? If you kind of go up and then over. That's 3 seconds. So if we take a look at the starting point of the reactants, you look at the distance between here and here, between the beginning and 3 second mark. You have this amount of change in concentrations going down by this amount. But if you take a look at the product side, the blue line here, the beginning compared to 3 seconds, look how much greater this value is. It's double. It's double the amount of this. So that's what the coefficients are showing you here, that your hydrogen iodide is being produced twice as fast as your iodine and hydrogen are being used up. All right, so let's take a look at how we can calculate rates. Number one, we can calculate the average rate, which is kind of what we've been discussing up until this point. You have your change in concentration over time. And if you were to graph it, you get a slope of a line. Now, you also have the instantaneous rate. Instantaneous rates are found by using the tangent to the curve at any given moment in time. So in other words, if we go back to our graph, if I want to find the rate at one particular moment in time, let's just pretend that this is, I don't know, 7 seconds. At this moment in time, well, we take a look, the tangent would be the line that comes across like this at that point. And then if you compare that with maybe, I don't know, 2 seconds, right, which would be the tangent would kind of come like this. This one is more steep than this one, right? This slope of this line here would be steeper than this one. So the rate is going to be greater here versus over here. So it's going to be a faster rate at the beginning. And if we look at the initial rate, which is the instantaneous rate, same as this, but at the moment the reactants are mixed, which is at the very beginning, before any products are created, that would be way here, right here at the beginning. That's the steepest line of all, right? That's when the reaction would be happening the quickest. And so this is very useful for us because when we look at rate law equations, which we'll get to on our next unit, or not our next unit, but our next section of this unit, by doing it at the very beginning, you don't have to worry about adding product concentrations into the equations simply because there are no products being made yet, right? This is the very beginning. This is at 0.0 seconds when you're first putting the reactants together. There's no products being made yet, so therefore you don't have to worry about having concentrations of products in the formula. So we only have to deal with reactants. Okay, and I think that's close to being it right here. Just one last thing we'll talk about is if you wanted to solve for rates, we can use an equation such as this, and this is very much related to the chemical equation and the coefficients that are used in the chemical equation. So here's the change in concentration of iodine over time, right? That's just your rate of iodine, how it changes over time, and it's negative, right? It's negative because you're using it up, right? These guys both are being used up as you create this. So both of these guys are negative. You're changing hydrogen over time, and you're changing iodine over time are both negative because you're using them up. And then this is positive simply because you're creating this, okay? Now notice the half here. Well, the half is because of the coefficient 2. Remember, you have an invisible 1 here, you have an invisible 1 here, and then you have your coefficient of 2. It's a 1 to 1 to 2 mole ratio. So really what that means is, well, if you think about it mathematically, well, what is 1 equal to? Well, isn't it equal to half of 2? Right? Isn't that what 1 is equal to? It's equal to half of 2. Right? So when you have a 1 to 1 to 2 ratio like that, when you're comparing this here and this here, right, like we have in this section, 1 is equal to half of 2, right? And that would make the equation true. So that's why we have a half here. So all in all, you take your coefficients and you put them in the denominator as a fraction, right, with 1 on top. Right? That's how you would do that. So let's just pretend, I know this is not how it would balance out, but let's just pretend, let me get rid of this. Let's just pretend that this was a 3 over here. So it's a 1 to 3 to 2 ratio. I know it doesn't balance, but let's just pretend that this is the way it worked out. Well, then this would still be the same, right, because it's just 1, right, 1 over 1. And then this is a 3, so this would become 1/3 times this rate, okay? And then this would still be 1 over 2 because you have a coefficient of 2 over here. All right, so that's how you would work that out. So whatever the coefficients are, that becomes the number in the denominator when you set this up. So if I know one value, let's say I know the rate of hydrogen, well then I can find out the rate of this, or I can find out the rate of this because they're all equal to each other, right? So that's how that plays out. Okay, so we're going to stop here, and we'll make another support video for what comes next in the notes, and then you can look at that video. We'll post all of this onto the calendar that's posted on the website, and we'll have links to that. So you can use it. You can scrub forward, scrub backwards, watch it as many times as you want. Speed it up if you want. Watch it at double speed, to get to the point where you're looking for it, and slow it down. And hopefully this will help. All right, guys. Till next time.